Hello everyone, welcome back. Let's move onward into chapter 14 where we deal with gas mixtures. So, what do I mean here? Well, simply put, we've been dealing with just steam or just freon or just air. But how do I deal with a mixture of gases? So, I'm not going to go into the too nitty-gritty here, but we're going to figure out how to deal with some of the important properties for these gases. So, if we're going to do that, the first thing we need to know is the composition of that gas. Like, what is it made of? How much of each individual component do I have? And so there's two ways of describing this. First off, you can do molar analysis. Simply say, how many moles do I have? Think of this more as just a direct count. I've got 15 oxygen atoms. I've got 20 nitrogen atoms. Okay, I've got more nitrogen than oxygen. But I can also do gravimetric analysis, where I'm simply saying, well, yes, I have more, let's just say hydrogen, than I have oxygen. However, hydrogen is tiny and oxygen is comparatively big. And so, like on a mass basis, I've got a lot more oxygen. So, for both of these, I can then calculate either a mass fraction right here or a mole fraction. Where the mole fraction is simply how many moles of that individual component over the total number of moles. And the mass fraction is simply that mass of the individual component over the total amount of mass. So not terribly difficult to calculate. For most problems, it's really just doing the same thing over and over and over again. So with that, you have a way of looking at these things and figuring out what the mixture is. And you will see both. As a note, if I add up all my mass fractions, they should add up to 1. Same thing for my mole fractions. Otherwise, you didn't add everything up. Okay, so here's one example. I have hydrogen, I have oxygen, and I'm going to put that together into a mixture. So I take 6 kilograms of hydrogen, 32 kilograms of oxygen, and I put them together, I have 38 kilograms. So my first question is, well, what is the mass fraction for these? Well, we'll start with oxygen. So oxygen, we have 32 kilograms of it. That's this part. And there's a total mass of 38. That's this part. So if I want to figure out the mass fraction for oxygen, it would simply be 32 over 38, or 0.842. So that's about 84% by mass oxygen. Okay, now let's do mole fraction. So in mole fraction, as a note, this is the exact same setup, just now in moles. 1 kilomole of oxygen, O2, molecular oxygen, is 32 kilograms, and 3 kilomoles of hydrogen is 6 kilograms. So this is the same setup. We're going to get very different results here because now we're just doing on a count basis, not on how big they are, just how many there are. And so what's the mole fraction of O2? Now, are the mass and the mole fraction the same? The answer is no, because now my mole fraction is just 1 over 4 for oxygen. And so that's only 25%, go down from 84% to 25%. So you can see that how you determine the mixture is going to really change the percentages here. So they're not just interchangeable. But if you know one, you can calculate the other. That's also fine. Okay, so let's pick out some helpful equations here. Boop, boop. And finally, boop. There we are. So like I said, is if you want to figure out your mass fraction, well, in terms of your mole fraction, you can do that. So like right here, this is showing how I can connect my mole fractions and my mass fractions together. If I know one, I know the other. I just need to know what my molecular weight of that particular component is. The capital M is molecular weight, the lowercase m is mass. So if I know the molecular weight of my particular component, and I know the molecular weight of my mixture, that's an average, I can solve for that. The next question you might ask yourself is, well, how do I find the molecular weight of the mixture? Well, that's up here. And there's various ways of getting it. So I can either do this in terms of my mole fraction or my mass fraction. Okay, it's the mole fraction or the mass fraction. In general, it's simply just what's the mass of my mixture over the number of moles in my mixture. Okay, that's how you can get it if you know those things. But usually we know something like on a per mole basis or a per mass fraction basis. And so that's the case. We're going to come down to here. And so it's simply a sum. Well, it's like weighted average. I'm saying what's my mole fraction? That's kind of like the weight. And then finally, what's the value? I multiply all those together, and I add them, and I get my molecular weight of my mixture. And I can do a very similar thing for mass fractions. So once you have that, you can go back and forth. If you know one, you know the other, and you can solve for both. Final little detail here is my gas constant. Remember, your gas constant has always been based on the molecular weight of the gas we're dealing with. For air, that's the molecular weight of air, which is around about 14. It's not quite. And we were just taking our universal gas constant and dividing it by that molecular weight. For hydrogen or helium or something else, it would have been different. But now we're going to have mixtures, and so we have to find the molecular weight of that mixture. And so we're going to be required to constantly go back there and find that molecular weight again and again and again in order to do this. Okay, so next slide's an example, so we'll stop here for now. We'll jump into that example next time. Thanks for watching. I'll see you all later. Bye-bye.